Good afternoon. My name is Troy Talent. I'll be presenting the spray paint booth pressure control system. With me presenting today also is Garrett Mitchell, and the other members of our team are Bradley Turner and Daniel Stoker. An outline of what I'm going to be talking about is our system background, description of it, the SSOC results, and the step function results, our FOPDT theory, and the model theory that goes with it, then our frequency response, and then Garrett's going to talk to you about the relay feedback, the results, and give a conclusion. Here's a schematic of our system. See, it has a variable speed motor right there. It goes into 3 boosts. You control the pressure. All the boosts don't have to be open at the same time. See our block diagram. Got our input, motor percent power, gives a boost pressure output. Like I said, not all boosts are used at the same time. The task is to determine the relationship between the pressure in the rooms and the speed of the blower motor. So this is an example of how we constructed our SSOC, just one of the plots we took. It's at 40%, pressure at 40%. So it comes to steady state about after 10 seconds or so. And here is our SSOC. It had 2 linear sections right here. The slope was 0.8% per centimeter H2O. And the upper range of 80 to about 95 with 0.24 slope. Alright, example of a step-up function. See our step input, we're at 15% on this one, 55 to 70. T0 came out to be 0.1 second. Our tau was 1.74. And our K that's gotten from the change in M over the change in C over the change in M came out to be 0.18 centimeters per H2O. Here's the K average for each of our low and mid and high ranges. See, K goes up as the percent motor input power goes up. Here's T0 average. I don't know why T0 is so low here and this one's so high. Here's our average tau. And then we did for the theoretical modeling. All those were for our experimental. This is for our theoretical FOPDT. There's our transfer function that we used. And we took our results and we graphed them over our experimental. These were our approximate parameters that we wanted to match. 15 seconds. Amplitude of 15. Gain of 0.18. Dead time of 0.01. 1.7 time constant. 85% for our input and output 3.5 centimeters H2O. Here's our model. The red line is our model output. The green line is our experimental output. And we matched them over the 15% step. And here's an example of the step down. Do the same thing. Model output and the experimental output. Same range. Here's our model K average. Also goes up as the percent increases, just like the experimental did. T0 with the uncertainties here. Still has the high at 75 to 85%. Here's our tau average. And here's our overall average results. FOPDT parameters for the experimental. T0 was 0.18 seconds plus or minus 0.03 seconds. Tau is 1.44 plus or minus 0.05 seconds. For the model, T0 was 0.2 plus or minus 0.9 seconds, 0.09 seconds. And tau was 1.42 plus or minus 0.1 seconds. Alright, so for our frequency response, It's a time versus our input, percent and for our input, sine wave, and for our output we have centimeters H2O oscillating. So your input is A sine omega t, t, and the output has a phase angle shift. Here's an example at 0.1 hertz, one of the 9 frequencies we ran. The green is our input. You see, our chain at DM is from peak to top peak to bottom peak for green, which was 10 consistently on each one, and DC fluctuated. Here it's 13.6 to 10.9 approximately, and DC over DM gives you your amplitude ratio. Here's one of our Bodie plots, the log. Got your amplitude ratio versus your frequency. It's pretty. It's got one more point. It's kind of messed up here. And here's the phase angle versus frequency. Semi-log though. And here they are together. This is how we obtained all our experimental values for our KCU and our order. So ultimate frequency, our K was taken from the first point, point 0.35 or so. FU was the ultimate frequency, minus 180. Phase angle, bring it up. The line, I think I'm going to the line over here, but it's supposed to be right there. It comes out to be like 1.5. And our order was right here on the last part of the first Bodie plot. And 1 over KCU is where you can take get the FU from actually. And here's all of our lists of results for each region. Daniels region, we got K to be 0.21. Our order was negative 0.06, probably a first order. FU was 1.5 cycles per second. KCU was 18.2. Tau was 1.1 seconds. T naught was 14.5 seconds. For my region, omega was 0.19. K percent for centimeters H2O was 0.35. Units right there. Percent centimeters H2O. Order -0.05. FU was 1.5 for mine. KCU was 38.5. Tau was 2.35 seconds. And T naught was 19.2 seconds. Our point A, which Garrett will explain later, our tau and T naught turned out to be way higher than it should have been for Daniels and I. And this is for our model portion of the sine, our transfer function that we use to then we get the graph. We got our data from the graph over the experimental to compare. Here's our first plot with the uncertainty. The red line is the model, and the blue dots are the points, the experimental points that you saw earlier on the Bodie plot. And here's the second one, phase angle versus frequency. Same thing, red line is your model, blue dots are your experimental points. Here is Daniels and I's together. The red and blue are mine, and the purple and green are his. This is very strange right here. It's green dots. Not really sure why that happened. Might have been some uncertainty with Daniels' numbers there, but while he was doing his amplitude ratios and phase angle. That's for the amplitude ratio versus frequency. This one's for phase angle, same thing, versus frequency. And here are our graphical FOPET parameters for both the regions. K percent, 0.21% for centimeter H2O, 0.13 seconds for T naught, and 1 for tau. I think that's supposed to be 0.2 for tau right there. 85 and 100%. K is 0.3% centimeter H2O. T naught is 0.2 seconds. Tau is 0.7 seconds. And those are the accurate model T0 K and tau value. And Garrett will talk about the relay.